Most hikers assume the glitter in trail dust is just quartz, or sometimes even ice, catching the light. But one fragment found along a shaded California footpath refused to melt in hand, refused to scratch under pressure, and sent an unusual chill down a field collector's spine, not from cold, but from thermal behavior. The sliver in question was neither water nor the more familiar quartz. It was something far rarer. This is where most casual observers miss the first signal: how true diamond reflects light not just with brilliance, but with a deep adamantine luster that quartz never matches, and a hardness that resists abrasion even against fine sandpaper. The mistake stems from how both quartz and diamond can appear glassy and colorless, especially in rough form. But there's a quick way to separate them in the field. Most notably, weight in hand. Quartz has a specific gravity around 2.65, while diamond is closer to 3.52. The difference is subtle, but when you're accustomed to handling minerals, the increased heft of diamond becomes intuitive. Then there's habit. Diamond often presents in a rough octahedral shape, with smoother faces than quartz and no conchoidal fractures. Ice, of course, evaporates. But on a warm afternoon, the glinting specimen simply sat in a dry palm, cool to the touch and unmoved by time or temperature. What was most telling, however, was light behavior. While quartz often scatters internally with a smoky or clouded glow, this specimen refracted with brutal clarity. Under loupe magnification, the edges remained clean and geometric, no facet doubling, no bubbles, no cleaving hints. And when rubbed against 6 sandpaper Mohs 9, it left the abrasive unchanged. Quartz would have powdered. Still, skepticism persisted. Could this be high-grade glass, moissanite, or even a polished zircon fragment? Only deeper field testing could confirm the suspicion. But the hiker had already unknowingly passed over other clues. Dark specks in the gravel, too heavy for mica or feldspar, scattered like iron filings downstream. What else was lying underfoot, overlooked? Most people rely on color or clarity to judge a stone, but what truly separates an ordinary pebble from a potential diamond is behavior under stress and light. The next day, under more controlled lighting, the same sliver that wouldn't melt began to show features inconsistent with quartz or glass. Its luster was unusually sharp, not just shiny, but with a kind of deep internal fire that held even when dusty. Held up beside known quartz, the difference was immediate. Quartz offered a milky gleam. This candidate refracted light with a brutal, almost metallic intensity. Another quick test, edge response. The fragment was lightly pressed into a piece of copper wire. No scratching, no marks. Quartz, with its Mohs hardness of 7, would have shown at least surface resistance. But this piece shrugged it off. Even ceramic couldn't mark it. At this point, the candidate had passed 3 visual behavior tests: luster, weight in hand, and scratch resistance, that together built a compelling argument for further evaluation. Then came habit, the geometry of its shape. Diamonds typically form as octahedra, though often distorted or rounded. This crystal had 4 visible faces converging to clean terminations. Glass rarely forms such regularity in nature, and quartz habit tends towards 6-sided prisms or irregular lumps. Furthermore, the piece lacked any bubble inclusions, a common giveaway in synthetic or glass imitations. In transmitted light, it remained colorless and flawless to the eye, which could suggest either a very pure diamond or a cunning simulant like moissanite. But moissanite gives itself away electrically. The hiker, now intrigued enough to test deeper, used a basic diamond tester, a thermal conductivity probe. The needle spiked immediately, suggesting high thermal transfer consistent with diamond. However, moissanite also conducts heat similarly. What it doesn't do is conduct electricity well, and that would be the next test. For now, the specimen had survived every common field elimination step. What hadn't been considered yet, however, was context. If this truly was a diamond, how had it ended up on a California hiking trail? The surface clues were mounting, but without geological reasoning, the odds felt remote. That's when the map came out, and a series of overlooked mineral clues began to trace a path upstream. California isn't the first place most people associate with diamonds, yet the state has quietly harbored the right ingredients for millions of years. Volcanic arcs, ancient subduction zones, and deep crustal activity all intersect here. And in rare cases, they brought up the right kinds of pipes. Most are buried or eroded, but placer deposits can carry the story downstream. The trail where the fragment was found cuts through a weathered alluvial corridor, shaped by thousands of years of seasonal runoff and uplift. This terrain acts like a natural sieve, concentrating heavies in predictable pockets, but only if you know where to look. To understand how a diamond could end up there, you need to trace its likely path. Diamonds form deep, over 140 kilometers below the surface, and only reach daylight when carried upward by explosive volcanic eruptions through kimberlite or lamproite pipes. While California lacks well-known active pipes, remnants of these systems do exist, often misidentified or buried under younger sediments. In the Sierra foothills and parts of the Klamath Mountains, geologists have found kimberlitic dikes, lamproite traces, and mantle xenoliths, evidence of deep transport events in the distant past. More importantly, California's complex tectonics mean erosion and deposition have played a long game. Rivers like the Feather, American, and Yuba have carved through ancient channels and redistributed mineral content. Placer gold is well known here, but heavier stones like garnet, chromite, and even diamond sometimes travel with the same flow logic. Meander bends, inner curves, and tailing zones are ideal catchments for dense material. And the dry creek crossing where the stone was picked up? A textbook paleochannel exposure, now a popular shortcut for hikers. One detail stood out: the absence of surrounding quartz veins or visible pegmatites, which often accompany quartz and feldspar-bearing rocks. Instead, dark, ultramafic outcrops nearby hinted at serpentinized peridotite, the kind of host rock that can indicate a deeper magmatic source. That changed the plausibility calculation. If this was indeed a transported diamond, the feeder zone had to be somewhere within erosion range. But diamonds rarely travel alone, and one type of mineral, often overlooked, was about to reappear in the trail dust: pyrope garnet. The red grain looked like nothing special, a dull, slightly translucent speck trapped in a pan concentrate. Most would discard it as common garnet, a regular feature in metamorphic terrains. But under magnification, its purplish hue and perfectly dodecahedral shape hinted at something more significant: pyrope garnet. Unlike almandine or grossular, pyrope is a high-pressure mineral associated with ultramafic rocks, and more importantly, with diamond stability zones deep in the mantle. Its presence, especially when fresh and unaltered, is one of the first diagnostic indicators that you're in a potentially diamond-bearing system. Alongside the garnet, other dark heavies began to appear in small amounts: grains of ilmenite, magnetite, and a few chromite fragments. These aren't valuable on their own, but as a suite, they're telling. Known as indicator minerals, this cluster is a standard signal used in diamond exploration. Each has a high specific gravity, making them easy to isolate in a pan or sieve, and each survives long transport from a primary pipe. When found together, especially in alluvial settings, they suggest proximity to a kimberlite or lamproite source. The magnet test provided another confirmation step. Sweeping a strong magnet over the dry concentrate immediately pulled several black grains aside. Most likely magnetite or ilmenite, both key indicators. Chromite, while non-magnetic, can be visually separated by its metallic luster and high density. At this stage, the hiker wasn't just chasing a rogue diamond anymore. The supporting cast of minerals was assembling, and their presence suggested a geological context consistent with secondary diamond deposition, a placer system, not a fantasy. It's worth noting that not all garnet-rich gravels point to diamonds. Almandine, especially from metamorphic schist belts, can mislead with similar color. But pyrope has distinguishing features: higher refractive index, a deeper raspberry tone under daylight, and lower iron content. In some regions, microprobe analysis is used to confirm composition, but in the field, a handheld spectroscope and clean fracture face can give strong hints. Finding just one or two of these indicators wouldn't mean much. But here, multiple appeared in a short pan session from just a few liters of trail dust. That density and the mix of types turned a speculative curiosity into a credible lead. Now came the question, could a more systematic sample grid confirm a pattern, or was this just a concentrated fluke downstream of a long-buried source? Just a few centimeters below the trail surface, the creek gravel shifted from pale, angular quartz to a darker, heavier matrix. This was the ideal collection zone, a natural trap where slower-moving water once deposited dense materials. Using a number 20 mesh sieve, almost equals 0.85 mm aperture, the hiker began isolating concentrates from a 5-gallon sample. The goal wasn't volume, it was resolution. What survived the sieve would be the heaviest and most durable material in the flow. What emerged was a mix of black sands, garnet grains, and a handful of unusually bright crystals, angular not rounded, and distinctly harder than the quartz dust surrounding them. The key technique here was visual stratification. By drying the concentrate and spreading it on a white tray, subtle color differences and shapes became visible. Deep red garnets, metallic flecks of ilmenite, and a few water-clear fragments that held geometry even under rough handling. Ice would have melted hours ago. Glass would have dulled or chipped. These fragments had edges sharp enough to catch on skin. Next came the magnet sweep. A neodymium magnet passed just above the tray, pulled several grains out. Clean magnetite and ilmenite response. Then, using a small vial of heavy liquid bromoform substitute, the hiker performed a simple density flow test. Quartz sank slowly. The suspect crystal remained suspended, suggesting a density around 3.5, within diamond range. Not definitive, but more than enough to justify the next step, site replication. The test site was marked with GPS and photographed, including pan angle and sun position for repeatability. Then a second pan was taken 5 meters upslope and another downstream. The upstream sample held fewer indicators. Downstream, the ratio improved. This hinted at a point source origin just above the original collection, a place where erosion might be exposing deeper materials. On-site erosion cuts revealed patches of ultramafic rock fragments embedded in oxidized clay, serpentinite-derived and flecked with darker minerals. One of the pan's final pulls brought up something that looked nearly octahedral again, small, clear, and unblemished. But its edges were oddly rounded. Could this be a worn diamond or something else entirely? A thermal tester would help, but it wouldn't settle everything. For that, electrical conductivity and refraction checks would be needed, and a better understanding of what moissanite, zircon, and quartz can mimic under pressure. The mystery was deepening. A thermal conductivity tester can't lie, but it can mislead. Back of the trailhead, with a fresh battery and stable temperature, the hiker placed the suspect octahedral fragment on a ceramic tile and gently pressed the probe of a portable diamond tester against it. Within seconds, the needle spiked past the diamond threshold. A second test repeated the result. For a moment, everything aligned. Thermal behavior matched diamond. Hardness had withstood 6 sandpaper. Density floated in the right range, and luster remained adamantine. But here's the problem. So does moissanite. Moissanite, a lab-grown silicon carbide, conducts heat nearly as efficiently as diamond, enough to fool thermal probes entirely. And it's increasingly common in jewelry and synthetic markets, with occasional loss or discard into soil systems near recreation areas. Field misreads happen when pieces of moissanite, which also resist scratching and resemble diamond in clarity, find their way into gravel from runoff, trail litter, or repurposed fill. To clarify the result, an electrical conductivity test is the critical next step. Moissanite conducts electricity. Diamond does not. In lab settings, this is easy. In the field, it's more complex. Lacking a probe for that specific test, the hiker shifted to a loop inspection. Under 10x magnification, facet doubling, a hallmark of moissanite's double refraction, can appear. Diamonds, being singly refractive, show crisp facet edges. The crystal under inspection? No obvious doubling. That slightly favored diamond, but wasn't yet conclusive. An alternative method available on site: light behavior through immersion. By placing the crystal in a small vial of refractive oil or water, the optical boundary behavior could be observed. Glass or quartz often vanish into the medium due to lower refractive indices. Diamond retains its outline sharply. In this case, the candidate held its edge, another point for diamond. The ambiguity still lingered. With 2 positive indicators and 1 remaining test out of reach, the smart move was escalation, not conclusion. The hiker documented the specimen's features in detail and prepared for grid sampling. If this was real, it wouldn't be alone. Diamonds travel in erosion lines, not isolation. A pattern would tell the truth faster than a single fragment ever could. And grid sampling, done correctly, would reveal whether this was an isolated fluke or the leading edge of a buried concentration zone. Grid sampling doesn't just reveal patterns, it makes the invisible map visible. Using a 3 by 3 meter layout, the hiker divided the surrounding creek and bank into 9 equal quadrants, each flagged with biodegradable tape and GPS marked for exact location tracking. From each cell, a controlled volume of sediment was extracted. 5 gallons dry, screened through a number 20 mesh, with concentrates stored separately. The goal: identify where indicator density peaked and whether more diamond-like fragments repeated across space. Each sample was processed using the same field protocol: magnet sweep first, then drying, then visual stratification on a white tray. In cells 1, 2, and 3 upslope, indicator counts were low, sparse garnet, almost no ilmenite, no clear candidates. But in cells 4 and 5, which straddled the original find, the picture changed. Here, garnet counts rose sharply, more than 15 visible grains per pan, many showing classic raspberry hues and dodecahedral faces. Ilmenite response increased under magnet, and a few chromite grains were visible, shiny and black with a metallic tint. Most striking was cell 5. Among the heavies, another clear octahedral crystal emerged, smaller than the first, but geometrically cleaner, with perfectly formed edges and no visible inclusions. Unlike the earlier piece, this one showed slight frosting on one face, possibly from abrasion. It passed the thermal test again, and when viewed under loupe, still no facet doubling appeared. This was the first strong repeat, suggesting a source more than a fluke. The downstream cells, 6 through 9, showed a tapering effect. Garnet and ilmenite counts dropped, though traces remained. This gradient further supported the idea that cell 5 marked a deposition focus, the highest local concentration, likely caused by a microdepression or eddy point during seasonal runoff. Now came the record keeping. Each sample bag labeled by grid cell, photologged, and kept separate to preserve provenance. These were not just for field verification. They'd guide lab work later. The grid itself told a story. A tight cluster of indicator minerals and 2 diamond-like fragments centered on a 1 by 1 meter patch. That level of focus meant either a localized erosion exposure or proximity to a still intact feeder rock. But one find in the next pan complicated the picture. It looked perfect, possibly too perfect, yet slightly soft-edged. What made it through the sieve didn't pass the weight test in hand. Something was off. It had all the right moves, clarity, octahedral shape, sharp lines. But when held between 2 fingers, the newest crystal felt light. Not weightless, but off. The density in-hand test, as subjective as it is, flagged a discrepancy. Compared to the earlier fragments, this one lacked the subtle heft that true diamond carries. Still, it resisted scratching, sparkled under angled light, and didn't melt. The inconsistency was subtle, but enough to warrant closer scrutiny. Placed under loupe magnification, the crystal's edges told a different story. Where the earlier candidate had crisp, clean terminations, this one had rounded junctions and tiny pockmarks. These weren't signs of transport wear, they were signs of manufacture, likely glass. Its high clarity and shape might fool a casual observer, but under trained eyes, the surface tension betrayed it. No growth lines, no internal zoning, and most telling, a slight blue tint at the base, almost invisible unless viewed in backlight. That hue was a hallmark of some types of leaded glass used in simulants. To confirm, a UV flashlight test was applied. Genuine diamond often fluoresces blue under long-wave UV, but glass typically glows dull or not at all. This fragment gave a faint greenish fluorescence, a warning flag. Further, the thermal probe barely registered it. It failed to spike the way the previous fragments had. In short, this was the first clear false positive. A diamond simulant, likely man-made, possibly introduced into the trail environment via human activity. False positives are part of the process. What matters is recognizing them before they escalate cost or reputation risk. Glass, quartz, and high-index simulants like yttrium aluminum garnet, YAG, often pass basic visual tests. That's why stacking indicators, luster, habit, hardness, density, thermal, and electrical conductivity is essential. No single test is conclusive alone. This fragment's presence raised a troubling possibility: contamination. If simulants were present, either naturally washed in from industrial sources or discarded intentionally, they could distort the field data. It would mean redoubling verification steps and isolating only those fragments that passed all 6 indicator categories. Fortunately, the earlier samples, especially those from cell 5, still held. But the question now shifted from individual fragments to broader context. Were these indicators washed in from afar, or was the source local? And if local, what pipe or deposit could explain the suite without known kimberlite on any map? The lab confirmed it. The first 2 fragments, including the one from cell 5, were both natural diamonds. Not synthetic, not moissanite, not glass. Their identities were established by Raman spectroscopy, confirming the carbon lattice structure, specific gravity measurements, both 3.52, and visual confirmation under cross-polarized light to verify single refraction. But there was a catch. The crystal structure showed sector zoning, a pattern inconsistent with kimberlite-derived diamonds. Instead, the morphology pointed toward lamproite origin, a rarer volcanic host. This detail changed everything. California has no widely recognized diamond-bearing lamproite pipes, at least none formally mapped or exploited. Most known deposits of this kind exist in parts of Australia, Ellendale, or India. Yet the mineral suite recovered from the trail matched what's typical in lamproitic systems: abundant ilmenite, high chromium chromite, and magnesium-rich pyrope. This opened a new line of inquiry. Had a lamproite source been hiding in plain sight? The diamond's nitrogen aggregation state, measured by infrared absorption, suggested a type IAB classification, meaning it had remained in the upper mantle for a prolonged time before being rapidly brought to the surface. That rapid transport is consistent with explosive volcanic activity, again pointing away from slow uplift metamorphism and back toward deep source pipes. Further, trace inclusions in one crystal, tiny perovskite and enstatite, matched inclusions from lamproitic sources elsewhere. But the real shock was the trace element fingerprint in the garnet suite: elevated chromium and low calcium, a classic geochemical match to group 1 eclogitic inclusions, the kind that form in subduction-modified mantle lithosphere. This meant the sample not only contained natural diamonds, but diamonds from a geologic process unaccounted for in existing California mapping. Either the diamonds had been transported from elsewhere in antiquity, highly unlikely given the lack of large-scale glacial movement in the region, or a local undocumented lamproite or lamproitic breccia body existed nearby, yet to be sampled or described. That possibility reframed the entire find from oddity to lead target. The implications for mineral exploration were immediate. Lamproite pipes erode differently than kimberlites, often blending with surrounding rock due to their varied composition and weathering style. Many are overlooked as worthless volcanic breccia unless indicator minerals are actively sought. And here, those indicators, pyrope, ilmenite, and chromite, had been underfoot, ignored by years of foot traffic and runoff. But identifying lamproite without surface exposure is a different challenge. The next step required topographic analysis, looking for subtle geomorphic signatures, circular depressions, resistant knobs, or anomalous drainage that could reveal buried intrusions. Time was now critical. If a new pipe existed and hadn't been staked, the window to assess it was closing. What the topography lacked in drama, the geophysics hinted in silence. A review of USGS and State Geological Survey maps revealed a peculiar magnetic anomaly, subtle, donut-shaped, and long ignored, located less than a kilometer upslope from the grid site. Originally flagged as low-interest volcanic breccia, in a 1980s mapping expedition, it had never been reassessed with modern tools. But the anomaly's signature, a low magnetic core surrounded by a ring of elevated susceptibility, matched known lamproite outlines in other regions. It wasn't the shape of an ore body. It was the ghost of an ancient vent. Cross-referencing this with historical borehole data nearby revealed even more. A well drilled in 1973 for water rights recorded dark ultra-basic clays with weathered felspathoids at a depth of 16 meters, exactly the kind of alteration product found in decomposed lamproite. The well had since been capped and forgotten, and the land above it reverted to unmanaged public access. No claims, no fences, just trees and runoff. Armed with this data, the hiker, now acting more like a reconnaissance geologist, initiated a systematic soil sampling line across the anomaly. Each sample followed a tight 20-meter interval, screened for heavies and indicator minerals. By the third transect, the pattern was undeniable. Pyrope counts peaked over the magnetic low, ilmenite increased, and 2 new chromite grains, unusually sharp and fresh, appeared in the concentrate. None of this proved a pipe, but the clustering was consistent with an erosion dome or vent throat buried under soil and scree. Further downstream, additional trail dust samples showed diminishing indicators, matching the expected dispersal fan from a localized erosion source. The diamond fragments recovered earlier now sat precisely where one would expect them in such a fan, just far enough from source to be exposed by runoff, but not so far as to lose the supporting mineral suite. With lamproite as the working hypothesis, another test became relevant: potassium content. Lamproites are unusually rich in K-feldspar and lucite, even in their altered forms. Using a handheld XRF scanner borrowed from a prospecting contact, several exposed outcrops on the anomaly ridge were tested. Potassium readings spiked, higher than neighboring basalt or serpentinized rock. Though surface weathering muted the signatures, the mineral fingerprint was getting clearer. Still, no exposed breccia, no vent mouth, and no visible xenoliths had been found yet. But the clock was now ticking. Any credible sign of diamondiferous lamproite in California, previously undocumented, would draw rapid attention. Permitting, claim staking, and sample protection would become urgent. First, though, there had to be proof the terrain still held unweathered, in situ material. And that meant getting deeper, without triggering a legal boundary. Zircon is the great deceiver. In certain light, it flashes with brilliance indistinguishable from diamond, especially in river-worn form. And on a trail like this one, where volcanic and metamorphic terrains blend, zircon is abundant. It also survives transport well, clings to black sand concentrates, and resists moderate heat and abrasion. That's why any serious diamond verification process must include elimination of zircon as a false positive. It fools more collectors than any other mineral. The clearest field test? Specific gravity and optical behavior. Zircon has a density of 4.6 for 0.7 G/cm superscript 3, significantly heavier than diamonds, 3.52. A simple water displacement test reveals this. Submerge the stone in a graduated cylinder filled with water, note the volume displaced, and weigh the specimen. Even with field-level accuracy, a mismatch of more than 1.0 G/cm superscript 3 is easily detectable. When the hiker tested one particularly brilliant fragment, previously assumed to be a third diamond, the result came back at 4.65. It was zircon, despite having passed basic hardness and luster tests. Another trap is double refraction. Zircon, like moissanite, can exhibit slight birefringence. Under a 10x loop, edges of back facets appear slightly doubled, especially when viewed through the crown. In contrast, diamond, singly refractive, produces clean, undoubled edges. This test, while subtle, is fast and free. The hiker applied it to 3 ambiguous samples and immediately ruled out 2 more as zircon. Then there's the UV test. While some diamonds fluoresce under long-wave UV, zircon typically does not, or glows with a greenish tint. Glass, another frequent mimic, often remains inert or glows faint yellow. In side-by-side testing of 4 suspects under a 365 nanometers UV torch, only 2 fluoresced blue in the classic diamond pattern. The rest remained dark or tinted green. Even thermal probes offer little help against zircon. Although it doesn't match diamond's thermal conductivity, in cool outdoor conditions, the initial reading can be deceptive due to surface temperature fluctuations. A warm stone, pocket carried for hours, might misread high if not allowed to equilibrate. Ultimately, the best zircon test remains context. Zircon is often found with granite, pegmatite, and metamorphic schists, not with pyrope, chromite, or ilmenite. If you're pulling zircon but not the indicator suite, you're likely in the wrong terrain for diamond. This differentiation phase was critical. The hiker now had a refined tool set: thermal response, specific gravity, UV fluorescence, double refraction, and, most importantly, the presence or absence of supporting indicators. Every piece of field data now served to filter, not just to find. And with false positives being eliminated, the ratio of real signals to noise began to crystallize. But the proof wouldn't just lie in fragments. The real confirmation, the test no mimic could fake, would come with water displacement, a simple cylinder, and a few precise grams of truth. At this point, everything pointed toward a definitive test: specific gravity by water displacement. It's simple, reliable, and immune to surface tricks. The method involves measuring the dry weight of the stone, then its weight submerged in water. The difference reveals the volume displaced. Divide dry weight by that volume, and you get density. Diamond should return a result around 3.52 G/cm superscript 3. No more, no less. The hiker set up a basic field rig, a digital scale accurate to 0.01 G, a plastic cup of distilled water, and a loop of thread to suspend the specimen without touching the container walls. The suspected diamond fragment from grid cell 5 weighed in at 0.42 G dry. Submerged, it displaced just enough water to register a 0.30 G loss. The calculation: 0.42 divided by 0.42 minus 0.30 equals 3.5 exactly. Textbook diamond. Another specimen, a brilliant shard found downstream, returned a result of 4.67. Far too dense. Zircon confirmed. A third, slightly lighter piece, read 2.65. Quartz. By testing 5 suspect fragments, only 2 fell into the diamond-specific gravity window of 3.50 to 3.55. This method, while rudimentary compared to lab hydrostatic balances, was conclusive enough in the field to call fakes fast. The same test, applied to supporting indicator minerals, helped triangulate validity. Pyrope garnet landed between 3.7 and 3.9. Ilmenite closer to 4.5. Chromite pushed above 4.6. These numbers matched expectations, reinforcing that the concentrate suite wasn't random. It was consistent with erosion from a high-pressure source. Why is specific gravity so decisive? Because it bypasses optics and surface artifacts. A diamond may look cloudy, chipped, or discolored and still be real. Conversely, glass or moissanite might sparkle brilliantly yet fall outside the density range. This is one of the few tests that can be run in the field with near-lab reliability. Now, with 2 gravity-confirmed diamonds and a supporting mineral profile, the narrative tightened. This wasn't a one-off find. It was a dispersed microfield, a thin but real secondary deposit likely tied to eroding lamproite or deep-source volcanics. The question wasn't if anymore. It was how much. But another question loomed larger. What does a California diamond, especially one proven through field and lab methods, actually mean in the broader market? Is its value merely geological? Or could provenance amplify its worth beyond the stone itself? California diamonds aren't just rare, they're almost mythical in the gem trade. While the state is famous for gold, platinum, and nephrite, Authenticated native diamonds are so few and obscure that most dealers assume any mention is either a mislabel or a hoax. That scarcity is exactly what gives a verified find an edge. Provenance, the verified origin and journey of a stone, can sometimes add more value than clarity or carat weight alone, especially when that provenance rewrites part of the map. From a commercial standpoint, most raw diamonds under 1 carat, even with high clarity, fetch modest prices unless they come from a branded or rare source context. But the calculus changes when the origin is unique. The 2 verified diamonds recovered in this case were small, under 0.5 carats each, but their confirmed California origin, supported by indicator mineral sweet, density, thermal, and spectroscopic data, made them anomalies worth documenting. Auction houses and collectors prize geological firsts. In 2016, a 0.81 carat North Carolina diamond, modest in appearance but fully documented, sold at over 4 times the expected value simply due to its U.S. origin and scientific support. Similarly, Australian lamproite stones from Ellendale command premiums in certain cuts because they represent a closed, depleted source. If California lamproite or even a lamproitic placer can be established, the first stones verified from that setting could carry historic premiums. However, that potential value depends on proper chain of custody documentation. The hiker logged precise coordinates without publicizing them, retained original concentrates, and photographed each find in situ. Each lab analysis, Raman, density, UV, and XRF, was time-stamped and accompanied by specimen storage under controlled conditions. This type of evidence bundle matters not just for market value, but also for certification. Any future cutting, selling, or exhibiting of the stone would rely on this record to preserve its claim to place. Even rough stones of modest value, say $400 to $600 in normal appraisal, can reach 4 figures when tied to first-of-type localities. Museums, universities, and private collectors seek them for educational or display purposes. And with only a handful of historically recorded California diamond finds, most in the 1800s, new authenticated material could form the basis of a modern provenance line, provided the trail remains verifiable. But that value can also attract problems: lowball offers, resale mislabeling, and even fraud. Before even considering a transaction, another layer of defense was needed, confirming the stones not just as diamonds, but as untampered, non-synthetic, and unretouched specimens. And for that, independent lab certification was unavoidable. Owning a diamond is one thing. Removing one from the ground on public or unmanaged land is another. In California, like most U.S. states, mineral rights are legally distinct from surface rights, and unauthorized extraction, even of a tiny stone, can create serious complications if value is later proven. That's why before any further excavation or disclosure, the hiker needed clarity on access rights, claim potential, and what constitutes legal sampling versus illicit mining. The trail itself crossed federal land under the management of the Bureau of Land Management (BLM), not a state park or private parcel. That distinction matters. BLM land is often multiple use, and small-scale sampling for non-commercial geological purposes is allowed without a formal permit under the Casual Use Clause. But the moment you recover and remove a specimen with commercial potential, especially one proven to be a diamond, you cross into regulated territory. To protect the find, the hiker submitted a notice of intent to the BLM regional office, declaring the recovery of alluvial mineral samples under 100 pounds and clarifying no mechanical equipment or excavation beyond surface padding was employed. This document doesn't establish a mineral claim, but it legally acknowledges the activity. It also timestamps the find in case of future disputes. Next, a mining claim had to be considered. Under the General Mining Law of 1872, locatable minerals, including gemstones like diamonds, can be claimed through a lode or placer filing. The process requires boundary marking, a location notice filed with the county, and submission of claim details to the BLM within 90 days. The hiker marked a 20-acre placer claim over the suspected deposition fan, focusing on the erosion corridor centered on the grid-positive cell 5. Costs were minimal, just over $200 for filing fees, But the legal coverage was critical. It gave exclusive rights to the locatable minerals within the claim boundaries for as long as requirements, annual maintenance and filing, were met. It also created legal grounds for lab submission and future sale. At the same time, the hiker consulted with a mineral rights attorney to draft a basic chain of custody affidavit for the 2 confirmed diamonds. This document, paired with the grid sample data and lab certifications, ensured the stones couldn't later be accused of being synthetic, foreign-sourced, or improperly obtained. There were still constraints. No machinery, no digging below the surface without an environmental assessment, and no selling any material until the lab reports were finalized. But within those bounds, the find was now protected, both legally and commercially. The next critical task wasn't about stones. It was about tests, how to distinguish the last remaining wildcard, moissanite, from diamond in a way even a specialist couldn't misread. Moissanite is the ultimate curveball in field gemology. Nearly as hard as diamond, Mohs 9.25 versus diamond's 10, it resists scratching, sparkles intensely, and conducts heat, enough to fool nearly every low-cost diamond tester. It even mimics the octahedral habit in synthetic forms. That's why thermal conductivity alone isn't enough. To truly eliminate moissanite from the sample suite, you need a test it fails and diamond passes. Electrical conductivity. Diamonds are electrical insulators. Moissanite, by contrast, conducts electricity, especially when connected across the axis of its silicon carbide lattice. Using a simple 2-probe electrical tester, the hiker measured each remaining candidate from the pan concentrates. 2 that had previously passed thermal tests gave low, consistent electrical response, unmistakably moissanite. The verified diamonds? No signal. This clean binary result reinforced that thermal plus electrical testing together form the minimum credible suite for high-confidence field elimination. For less equipped fieldwork, there's also optics. Moissanite is doubly refractive. Diamond is not. Under a 10x loupe, look through the crown and observe the pavilion facets on the opposite side. If you see blurred or doubled facet edges, it's moissanite. If they appear singular and crisp, it favors diamond. While subtle, this optical test worked in daylight with a trained eye. 2 suspect stones showed slight doubling. They were removed from the candidate batch. Another trick involves dispersion. Moissanite splits light into spectral colors more strongly than diamond. This fire can appear too intense, even unnatural, under angled light. In one specimen, the hiker noticed this excessive rainbow flash. It was beautiful and wrong. Real diamond dispersion 0.044 is modest. Moissanite's 0.104 is over twice that, often betraying it under direct sunlight or LED. To further refine the sample set, the hiker subjected all remaining candidates to a high-intensity light comparison. Of the 10 clearest stones from grid cells 4 and 5, only 3 showed clean refraction, no electrical conductivity, diamond-consistent dispersion, and adamantine luster under field loupe. These 3 match the thermal and density profile already proven, making them the likeliest true diamonds. Why go to this level of detail? Because market buyers and labs will. Even one misidentified moissanite in a certified parcel can tank credibility, trigger legal issues, or invalidate chain of custody claims. The goal isn't just to find diamonds, it's to eliminate every reasonable doubt. And that moment was approaching fast. With verified samples in hand, chain of custody secured, and a provisional placer claim recorded, the hiker prepared to send the stones to a gemological laboratory for full certification. What came back next would not only lock an identity, it would influence price, rarity, and possibly rewrite the understanding of California's diamond potential. Certification changes everything. Without it, even a verified field diamond remains a curiosity, interesting but unmarketable. With it, that same stone becomes a legal, tradable asset with provenance, identity, and value. The hiker, now operating under a registered placer claim, selected the 2 best confirmed specimens for submission. Both gravity verified, thermally and electrically tested, and confirmed non-magnetic, with adamantine luster and no optical doubling. The destination, a US-based gemological lab with GI-trained staff and FDR, Fourier transform infrared spectroscopy capabilities. Each stone was submitted with a full supporting packet. GPS coordinates, generalized, not precise, field documentation, photos of the specimen in situ, test logs, and chain of custody affidavits. The lab accepted the package under a natural diamond assessment and origin review, meaning the stones would be examined for both physical identity and geological context. This process doesn't just answer, is it a diamond? It probes deeper. How did it form? Where did it come from? Is it synthetic? Treated? Transported? Initial results were fast. Both stones were confirmed as type Ia diamonds, nitrogen aggregated, with natural growth structures and internal strain lines consistent with high-pressure formation. One stone showed tiny mineral inclusions of olivine and enstatite, consistent with paratitic mantle origin. No signs of laser drilling, irradiation, or high-pressure, high-temperature (HPHT) treatment were detected. The second phase, origin suggestion, was more complex. The lab used trace element spectroscopy and infrared absorption to compare the stones to global diamond populations. The results were inconclusive for a known kimberlite source, but matched several diamonds previously recovered from lamproite-hosted fields in Australia and India. This aligned with earlier field observations and suggested the stones had not been transported far from their source. They were locally derived, not glacial erratics or alluvial strays from other states. With full certification in hand, the hiker now had a legally registered, scientifically supported find, the first such pair of fully documented California diamonds in decades. More importantly, the certification included a rarity note, uncommon U.S. locality with verified alluvial lamproitic indicators, limited comparative population. That phrase alone turned two small stones into showcase specimens. Auction outreach followed. Preliminary discussions with boutique auction houses and mineral galleries revealed interest, but also a pattern. Buyers were intrigued less by carat size and more by story, documentation, and exclusivity. If a few more stones of similar origin could be recovered and traced, this might evolve from anomaly into provenance line. But exposure brings risk. The market loves origin, and so do opportunists. As news of the find trickled out through informal channels, new footsteps began appearing on the trail near Cell 5. The real race had begun, not to extract, but to document, verify, and preserve what might be California's only known microfield of alluvial diamonds before overcollection or misinformation distorted its value. Transporting a certified diamond is one thing. Transporting an uncertified rough, especially with field provenance, is a legal and logistical minefield. Each step, from removal to storage, from documentation to laboratory handoff, had to be recorded with enough integrity to satisfy gemological scrutiny, legal inquiry, and potential resale partners. For the hiker, now acting as the de facto steward of a new micro-locality, the mission was preservation through rigor. The first move was specimen stabilization. Each candidate fragment was placed in a clear, labeled gem jar with foam padding and silica gel packets to reduce humidity. Labels included sample ID, grid cell origin, collection date, field test results, density, thermal, electrical, and indicator mineral co-occurrence. Each container was sealed and signed across the lid to ensure tamper evidence. This was critical. Any question about post-field modification would jeopardize authenticity claims. Next came the chain of custody log. Using a simple ledger format, every transfer was recorded. From field pack to staging case, staging to temporary lab, lab to courier, courier to final lab. Each entry included time, location, handler signature, and condition notes. Photos were taken at every stage, especially before and after lab inspection. For the two fully certified diamonds, even the X-ray scan images used during internal strain analysis were requested and archived. But the real asset wasn't the diamonds, it was the metadata. Alongside each stone, a digital dossier was compiled. GPS heat maps of indicator mineral density, sample grid diagrams, photomicrographs of pyrope and chromite grains, UV fluorescence logs, and all test values, both successful and failed specimens. This bundle formed the basis of what could eventually be a publication or locality brief. giving the site academic weight. Transport to auction evaluation, or a buyer requires one more step: customs and mineral export documentation. While interstate movement is unregulated for non-commercial finds, crossing state or national boundaries, especially with rough, uncut diamonds, triggers legal thresholds. The hiker filed a voluntary rough diamond declaration under U.S. Customs guidelines, even though the stones weren't leaving the country. This preemptive move, paired with certification, reinforced legitimacy. As insurance, the stones were photographed beside a size reference, under UV, and on a scale not just for sale, but to document them in case of theft or mislabeling. Only after all of this was complete were the certified stones stored in a bank safety deposit box, pending decision on cut, exhibition, or sale. What remained on the trail, however, was equally vital. Dozens of indicator-bearing concentrates, still unprocessed, had been stored under refrigeration and desiccant. The highest priority now was determining whether the field still held additional diamonds, or if erosion had simply delivered the last fragments of a vanishing pipe. And to answer that, the hiker needed data. Grid expansion sampling would begin again, but not just to find. This time, to measure depletion or confirm continuity. It began like before: scoop, sieve, pan, inspect. But this time the goal wasn't discovery, it was replication. If the earlier diamonds were flukes, grid expansion would expose the limits of their deposition. If not, the pattern would grow. Over 3 consecutive weekends, the hiker expanded the sample grid by 3 rows in every direction, pushing the original 3 by 3 meter layout into a 9 by 9 matrix, 81 cells, each sampled identically with 5-gallon buckets, number 20 mesh screens, and magnetic separation. Indicator mineral counts told the story first. In the outermost rows, pyrope garnet and ilmenite fell off sharply. Only background-level grains remained, common for mixed metamorphic terrain. But in cells adjacent to the original cluster, counts not only held, they increased. One cell, 6 meters upslope from the first diamond-bearing site, revealed 23 garnet grains in a single pan and 3 octahedral crystals within 2 hours of screening. One of these, under loop, showed sharp edges, no doubling, and a clean spike on the thermal probe. It tested negative on electrical conductivity. The most telling find came 2 grid rows upslope, a larger worn diamond fragment, 0.72 carats uncut, wedged in a clay lens just below a cobble layer. It lacked the clarity of the earlier pieces, slightly frosted and brownish, but passed every test. Density, 3.51. Thermal, optical, UV blue fluorescence. More importantly, it was physically embedded in situ, not resting on the surface or introduced by runoff. This ruled out trail contamination or foreign introduction. It was native, and it had been missed before only due to sampling boundaries. Over the full expanded grid, a total of 4 new diamond fragments were recovered, 3 under 0.5 carats, 1 just above 0.7. This changed the classification. The site wasn't a one-off deposit or trail contamination zone. It was an active erosion fan from a likely lamproite source, shallow, local, and still shedding trace stones. The data was now dense enough to prepare a formal field report. The hiker submitted findings, anonymized but location-specific, to a regional geological journal for peer consideration. The goal wasn't to broadcast the site, but to document a new geological signature: verified diamonds from an unmapped California lamproitic erosion system. Even if the pipe remained hidden, the fan proved it existed. This report had consequences. Local authorities began to see traffic spikes along the trail. Word of trail diamonds had begun circulating informally. One collector was spotted with a pan and cheap tester. Footpaths veered into the vegetation. The hiker, recognizing what could happen next, filed for an extended permit and requested limited area protection from the BLM under a conservation research clause. It wasn't about secrecy, it was about stewardship. A field this delicate, with so few data points and immense fraud potential, couldn't survive a free-for-all. Not if the goal was truth over treasure. Now came the question no pan could answer. What happens next to the site, the stones, and the story when a piece of unknown California ground suddenly matters on a global scale.